Hello everybody, thanks for the big assistance of this afternoon. I'm very glad to see you today. My name is Moal. I'm working for Shemar as a CTO and expert on technical insulation, external insulation products. I'm also working on the IEC working group TC36, which deals with insulators as TC36 chair, and I also deal with CIGRE working group, so A3 substation, B2 overhead lines, and D1 insulating material. Okay, so the presentation of today is about the HTV silicone rubber technology which is used on the composite insulator and regarding the applications on the substation insulators. So the content of the presentation is about the existing issues that are linked to the substations using traditional solution as porcelain. What kind of technical solution has been developed on the composite insulator, and what are the future possible developments. So, since more than 27 years, Shemar works on solution for external insulation and especially developed the products for substation, so hollow core insulator for substation application. And since about 15 years, there is a development also on composite insulator for transmission line, so like the cross arms and the suspension insulators. And this is the purpose of this presentation, as develop new formulation of silicone and new applications which deal that we can guarantee more than the 30 years and up to 40 years and more expected service life, as soon as you respect the right dimensioning and the right specification. So what are the existing problems that we can find in substation? First, linked to substation application, the top left photo is about explosion of a transformer bushing. So usually it's filled with oil and with porcelain insulation, and with any defects that you can have inside the bushings for transformer, it can lead to explosion of the porcelain. And the explosion with oil inside leads to fire, so it can destroy not only the transformer but also the big part of the substation. The second photo deals with the breaking links to earthquake or very high mechanical stress or short circuits. And the other issues that you can find, I would say, which are inherent to the property and the expectation from the insulator, is the rain and the pollution. So heavy rain or heavy pollution or ice, big ice, leads to flashover. So the composite insulator improves this kind of resistance. One very important topic for the future is the energy consumption. To produce porcelain or glass insulator, you need to reach more than 1000 degrees, and it means that very high energy consumption. To produce composite insulator, you need less than 150 degrees, and it means that you have much less energy consumption. For the same expectation, you need 5 times less weight of insulator. So it means that if it is 100 kilo in porcelain, it's about 20 or 30 kilograms in composite. And of course, the other issue of the life cycle cost linked to the usage of composite or porcelain insulator in substation is the maintenance. So the big advantage of the silicone insulation is to avoid any maintenance, since it is hydrophobic, so the property of the silicone remains excellent even if you have a polluted surface. When you have pollution on classic porcelain or glass materials, it leads to needs of cleaning because if you don't clean, then with the polluted surface and humidity, it leads to a high risk of flashover. So the maintenance may need for existing substation using porcelain, or aged porcelain and polluted porcelain is cleaning and spray RTV, but the costs are extremely high. So then the cost of maintenance is very high, and also you need regular inspection to check the performance of the insulation. So there is a long history of the development of the silicone insulation. First, it was in the 50s and 60s for medium voltage application, more with epoxy insulation. Then there was some development of shades in EPDM. Then RTV, low temperature vulcanizing shades in the 70s, LSR shades in the 80s, and since the 90s, the use of high temperature vulcanizing, so HTV, shades has been generalized for other lines and more use on substation application. The issues which was observed on first generation of silicone, RTV, LSR, and the first generation of some HTV was aging. So what does it mean aging? It means that you have a risk of cracking on the surface, of cracking and erosion on the surface, and then leads to catastrophic failure of the insulation. So to avoid that, you need to design the right formulation of material and to use the right material. So this table is not so recent. It has been made by Momentive, but it shows that you have three families of silicone insulation. One is RTV, so the raw temperature vulcanizing silicone. Second one is LSR, and the third one is HTV. So the tracking and erosion resistance, to make it short, is excellent for HTV due to the high rate of trihydroalumina, so fillers, ATH, which is used for the HTV. You don't have this kind of additives and fillers for LSR and RTV, which means that you have much less, lower performance in tracking and erosion. The issue that we see in the past, the bad design of silicone insulation leads to a bad image for the composite insulators. So this is also the challenge, is that we can show that we can reach very good performance with the new generation of insulators. So the technical solution, so we have seen the issues, and the studies leads to solution. So the explosion, so you want to get no explosion, no flashover. You need also to have more economical and more environmental friendly insulation. So you need to do studies to reach long life shed technology expectancy with HTV silicone, designing of composite FRP core. So the core can be for solid rod, pultrusion rod, or for hollow core, it can be, of course, it is filament winding tubes. But the raw material are the same, is glass fiber and epoxy resin. You need also to machine the surface of the tube and to make the assembly by crimping on solid rod or by gluing on hollow core. So you need a real good sealing technology to get also the tightness for the insulator. And you need also to have a good adhesion between the shed and the tube with injection molding process. So the key development and the key design is about the formulation. So you need UV aging resistance, you need high temperature aging resistance, and the first generation even of HTV shows some aging, and the major aging effect was much more about the hardening of the silicone. So then the lowest lower mechanical property after aging. So to avoid that, you need to use a specific formulation with reinforced fillers, and to improve this, I would say, UV and high temperature aging effects. The other parameters like tracking and erosion, resistance, so resistant to salt pollution, and sunstorm mechanical resistance is also part of the development. So to have a right silicone formulation is not enough, because during the process, so during injection molding, which leads to high pressure and high temperature, you have to apply the right parameters. So you need to have the clean surface to prepare for the adhesion of the silicone. You need the right bonding agent, but you need also the right process parameter, which means time, temperature, pressure, and then if you get this right recipe, then you get the right quality of insulator. So long life material technology, you have the factors, you have the solution, and to make short, to meet the long life expectancy, you need HTV silicone, high temperature vulcanization silicone, to reach the solution. So another slide that explains that if you don't have the right parameters, then you may have micro cracks at the surface, and then it will lead to, I will say, penetration of humidity that could reach the rod, and that is exactly what we want to avoid. This silicone oxygen energy explains that the reason why by design the silicone sheds are very good resistance for UV aging. So UV aging, acid rain, sandstorm, salt fog, corona. The corona, if you have, even on silicone surface, you may have some corona when you have accumulation of pollution and high humidity and also high electrical field. So you need to be sure that you reach, even during the design, the right corona protection by the grading rings to reduce the electrical field at the triple point, that you can avoid the corona, but also you need the formulation to be corona resistant. So process control, especially you need a very good and very automatized process control of the injection molding. So several patents have been developed regarding the process and the design. So this is a specific equipment which has been developed and I would say purchased by Shemar in our R&D laboratory. It's about thermal aging, UV aging, heat and humidity aging, acid rain and sun aging. So with this simulation on raw material or small reduced size insulator, we can use models showing that after accelerated aging test up to 5,000 hours, we can extrapolate the life of the insulator in severe conditions more than 40 years. So it's also important to dismount regularly the insulators which are installed in service to check their performance. So you have to check after dismounting that they have still very good performance. They keep the guarantee on flashover, I will say, electric test performance and mechanical test as new. So you have to check this by regular dismounting. This is a very specific UHVDC dismounting. This is described in our CIGRE A3 2024 paper, the kind of test that has been performed to check the good behavior after aging in very severe condition. This is showing some examples of combined studies which have been made with Chinese university, like CIGRE, Tsinghua University, to check that the performance of the insulator after some years of service are still fine. These slides show some examples of real applications since more than 10 years on 800 kV DC converter station. So you see some photos of reactor, air core reactor support, and also converter stations. So 1000 kV AC bushing, GIS bushing, 750 substations. So what is interesting is to see that even in very high altitude means less oxygen, so then you need higher arcing distance and you need better performance for the insulation. And also to show that the 750 kV Shazoo full composite insulator substation has been installed and since more than 10 years now, and it's 100% using composite insulators. So this also described in our paper. So strong wind and sun, seismic areas, high altitude, strong UV, high soil fog, extreme cold or extreme high temperature. So you can see all those kind of application, and you can see some, I would say, the major substations which are equipped with Shemar insulator in Moal, Chinese area. So this one we already talked about that. It's to the 750 kV Shazoo, fully equipped by composite insulator since 10 years. So to conclude, it's about the future development. So we need to work on, I would say, self-healing silicone rubber material, so new chemistry formulation to improve and to think about the next generation of the silicone. Also about this kind of HTV FRP tube, so how can we recycle it? So we have to think about that, how we can reuse some part of the materials at the end of the life cycle of the insulator after dismounting. So it's quite easy for the aluminum flanges, but for the HTV or for the FRP tube, this is more challenging. So this is something kind of field of research on which we are working on. Thank you for your attention.